So what we're going to work on here is an investigation of the solubility of a variety of compounds, which you can see lined up back, in two solvents: water, which is a polar liquid, and hexane, which is a nonpolar liquid. Now, for the purposes of this lab, I've just labeled my tubes with tape. So the water is the red tape and the hexane is the yellow. That's more so I don't get confused. I'm going to do these in the same order that they show up in the lab handout. I'll go through a few of them in some detail, but then I'll just show you the end result, because watching things dissolve is not super exciting. So the first one I'm going to do is naphthalene. So naphthalene is a nonpolar substance. I'll give you its formula for this one. Most of them you'll look up. Its formula is C10H8, and that makes it a hydrocarbon, and all hydrocarbons are nonpolar. So I'm going to take a little bit of naphthalene, put it in the water, give it a little shake, and you can see that down there at the bottom, the naphthalene is still there. So we would say naphthalene is insoluble in water. Try the same thing in hexane. Take just a small amount. Put it in, shake it up. And in this case, it's dissolved. So the nonpolar naphthalene did not dissolve in the polar water, and it did dissolve in the nonpolar hexane. Next up, I'm going to try an ionic compound, cobalt-2 chloride. So like I said, I won't be telling you every time whether things are polar, nonpolar, or ionic. So a little bit of cobalt-2 chloride. Into the water it goes. Shake it up. See if it dissolves. And I purposely chose this compound because cobalt ions have a color to them. So you can see here that the water's taken on the pink color of the cobalt ions. So cobalt chloride is soluble in water. Let's try hexane. Put a little bit in. Shake it up, and you can see it just sinks to the bottom. A little bit back down here behind it. Down there at the bottom, undissolved. I can shake it and it won't dissolve. Now, there are certainly chemicals that if you give them more time and more shaking will eventually dissolve, but you'll have to trust me on these. Next up, I'm going to do copper sulfate. So copper-2 sulfate is an ionic compound. Here I've got a blue crystal. So I'm going to do this in the two of them, and then we'll see what we get. Copper sulfate. You see the water's taken on the blue color of the copper-2 ion. So copper sulfate was soluble in water. Here's the copper sulfate in the hexane, and it's just sitting on the bottom completely undissolved. Next up, we're going to try iodine. So iodine is a purple-gray solid. Here's my iodine in water, and it's just sitting on the bottom undissolved. Here's my iodine in hexane. It's dissolved and the hexane's taking on a purple color. Next up, we will do heptane. Heptane is a liquid. So when we're dealing with two liquids, we'll often use the terms miscible and immiscible, which is Latin for mixable and not mixable, but they mean the same thing as soluble and insoluble. So here's my water, and I'll put this up to my sweater, and you can see there's a boundary where the water and the hexane have not mixed. Whichever one is on top or the bottom will depend on density. In this case, it happens to be the water. If you look in the hexane, there's no boundary. So the hexane and the heptane were completely miscible in each other. Next up, we'll try glycerin. Glycerin and water, no boundary. They're two miscible liquids. Here's glycerin and hexane, and you can see there's a boundary layer right here where my finger is, where the glycerin and the hexane do not mix with each other. After that, we're going to try glucose. Glucose soluble in water. It's kind of what you might expect, since it's basically the fuel for all of our cells, and everything on our cells is water-based. Here's the glucose in the hexane. You can see at the bottom of the test tube, it's just sitting there. I can shake it up. It'll make a suspension, sink back down. I can't make it dissolve just by shaking it. Now we're doing sodium chloride, table salt, highly soluble in water. And there's my hexane, and you can see down at the bottom, it's just sitting there undissolved. So far, what we've seen is that things tend to be soluble in one or the other. We haven't had any that are soluble in both, and we haven't had any that are soluble in neither one. Next up, we will try urea. So urea is the way that our bodies get rid of nitrogen-containing waste, which is the byproduct of protein metabolism. So since it's in our body, it probably makes sense that it has to be dissolved in water. There's my urea in water, dissolved. Here's my urea in hexane, and you can see at the bottom I have a bunch of pellets of urea that are not dissolving. After that, we're going to try lauric acid. So lauric acid is a long-chain organic acid. It has the formula CH3, CH2, 10 times COOH. It's a carboxylic acid, and even though it has an acid group at the end of it, the vast majority of this molecule is a nonpolar hydrocarbon chain. So here is my lauric acid in water, and it's actually floating on top. It's kind of a waxy substance. So even though this has a little bit of a polar characteristic to it, most of the molecule is nonpolar, and that kind of dominates its properties. Here it is in the hexane, dissolved quite nicely. After that, we're going to try pentane. Pentane's another hydrocarbon. You can see right there a boundary layer where the pentane and the water do not interact with each other. Pentane and hexane, no layer, they're miscible with each other. We use the term miscible because they're both liquids. Next up, we're doing palmitic acid. It's kind of a cousin to lauric acid. It's got 16 carbons rather than 12, but it's still primarily a nonpolar molecule, and it's also kind of waxy, low density, so it's floating on top of the water, but not dissolving. Here it is when I put a little bit in the hexane, it dissolves quite nicely. Next up, we're going to try pentanol. So here's my bottle of pentanol. It sometimes is called amyl alcohol. That's its old unofficial name. You'll see pentanol underneath it. It's got an alcohol group on it, so it can form some hydrogen bonds, but it also has enough hydrocarbon characteristic that it will not dissolve, and you can see the boundary layer. But it dissolves nicely in the hexane. So we've still got this pattern going where things either dissolve in one or the other. Here's some ethanol, sometimes called ethyl alcohol. Here it is in the polar water. It's miscible. And here it is in the nonpolar hexane. So this is a chemical that's soluble in both. It's kind of moderately soluble. It's close enough in polarity to the water that it dissolves or mixes, and it's close enough to the hexane as well. So we've broken our streak of things that are either or. Here's another alcohol, methanol. Here it is in the hexane. I did these out of order, sorry. does not mix with the hexane, but does with the water. And we're down to one more chemical. The last chemical we're going to do is calcium phosphate. This is an ionic chemical, so we're not surprised that it's insoluble in the nonpolar hexane. However, it's also insoluble in water. And we'll go over this a little bit in more detail, but essentially the ionic attractions, the ionic bonds are so strong that this chemical won't dissolve in either polar or nonpolar liquids. So while the like dissolves like rule is pretty good, it worked for the vast majority of these, it's not perfect. So here's just a little extra something. I'm doing this right before winter break, so here's my iodine and hexane, here's my copper sulfate in water, and if I pour them together, I can actually get this. So with the holidays coming up, I like to hang these on what I call my chemistry. Get it? Haha. So here we can see two alcohols, methanol and pentanol, that we used. Methanol was miscible with water. Pentanol, or is it sometimes called amyl alcohol, was not. Both of them have a polar OH end. But in methanol, the vast majority of the molecule is the polar end, and there's just a tiny amount of hydrocarbon. Remember, hydrocarbons are nonpolar. As this, what we call hydrocarbon chain, gets longer, that begins to dominate the properties of the molecule. So even though there's a little bit of an OH polar end here, the majority of this molecule is nonpolar, and it's insoluble in water. Ethanol was this. Which is just intermediate enough. It has enough polar characteristic and enough nonpolar characteristic that it was able to kind of violate the like dissolves like rule and be miscible in both. So here we can look a little bit at oil and water. Sometimes people say they repel each other, but that's not true. They simply have no reason to interact with each other. So here are some water molecules, the V shape. Remember, water molecules are polar. The oxygen end is slightly negative, the hydrogen end is slightly positive, so they can attract each other through hydrogen bonds. So all these water molecules are busy attracting each other. Oil molecules are nonpolar. They're hydrocarbons almost entirely. So they basically can't offer the water any reason to trade a hydrogen bond, which is favorable, for an interaction that doesn't have a charge. So because the oil has no charges available for the water to interact with, the water molecules simply continue to interact with each other, and the oil just kind of is not in the game, let's say. So here's what goes on when salt or any ionic compound dissolves in water. So remember, water, polar molecule, the oxygen end is delta minus, slightly negative, the hydrogen end slightly positive. So in an ionic crystal, you have a 3D arrangement of oppositely charged ions. These electrical attractions can be called the lattice energy. They're the strength of what holds the crystal together, and they're basically saying, stay together. Water, having some charges, can interact with these ions. So for example, a positive ion could be surrounded by water. The slightly negative end can attract it, and if the pull from the waters what's called the solvation process, can outpull the lattice energy, it'll go and dissolve. So it's kind of a battle. Lattice energy says stay together. Dissolving says float away. And then because dissolving increases the entropy of a system, and we'll learn more about that later, it's also favorable. So this section here is a little bit more for honors or AP. So this is going to relate to the lattice energy, and it's kind of governed by Coulomb's law, which says for any electrical charges, the force, in this case the attraction of the lattice energy, depends on a constant, the charges involved, and the distance between the charges squared. So if you look at this, the bigger the charges, the stronger the lattice energy. And that's why a lot of the ions that are +1 and -1 tend to be soluble, nitrate, sodium, potassium, ammonium acetate. But many of the ions with larger charges, carbonate, phosphate, sulfate, have many compounds that are insoluble. The larger the atomic radius or the ionic radius, the weaker the force. So really large ions tend to have weaker lattice energies. Okay. And yeah, that is a giant fly swatter, and you can never take too many chances.